Well, as a civil engineer, if you want to design a beam with some loading like this, obviously you have to design a section which can bear this stress caused by this load. So you have learned how to calculate that stress from bending moment. Based on that, you have find the cross section. Okay, but the design criteria for any civil engineer or structural engineer is not only your stress criteria. There is another criteria. What is that? Let's say you have to design this beam, okay, and this is under loading like this. After loading, what happens? It will deflect like this. Okay, if this deflection is too much, okay, let's say this beam under this loading deflect like this. So suppose this loading is coming from a car, okay, so is it desirable that the car or the driver will feel that it has deflected for this much amount? Obviously no. So the second criteria for designer is your deflection criteria. In this video we'll learn how to calculate the deflection of any member under any type of loading. Okay, so let's start. Before starting, I think you can recall the formula which we have desired already, which we have already derived during our bending moment and shear force relation, that the interrelation between bending moment, shear force or stress, bending moment and the curvature of the radius of curvature. That means if the beam deflect with some curvature with radius r, and the cross-sectional property, the material property or the Young modulus, you have already learned the interrelation. What is that? The famous formula, that is your may I follow you Elizabeth Rani. Okay, E is Young modulus, R is radius of gyration, F is stress, Y is the fiber, the distance of the fiber from neutral axis where you are interested to find the stress, M is the applied moment caused by your load, and I is the moment of inertia about neutral axis. Okay, and from this formula, if we combine these two, we can get that M by I is equal to E by R, and from that we can say that 1 by R is equal to your M divided by EI. Okay, so this is already known to you. Now if we can express this radius of gyration in terms of the deflection, then obviously for given material, that means Young modulus, or given cross section or I, or given loading or M, we can find out what is the deflection. Okay, so now consider a beam. Let's say this is our beam. Okay, now apply some load on it. Well, we are applying only a point load. After application of this point load, what will happen? Simply it will deflect like this. This is the deflected shape. Okay, so consider any section in this beam. Well, let's say this deflected shape is represented by your this curve. They are identical. These two are identical. Now consider any two section in this beam. First, let's say this is one section, that is section M, and here this is the M. Let's say this was your support, okay, and this was your actual beam. Now draw a tangent at beam. Well, it will be something like this. This is the tangent at M. Okay, and it will make some angle with the original beam. Okay, let's say this is your theta 1. Clear? Now again consider another section. Let's say this is n, section n, and this section is at a distance of x. In horizontal direction we will measure x in this direction, this is x, and we will measure y as positive in this direction. Okay, because in normal cases after applying load the deflection will occur in downward, that's why we will take y as positive in this direction. Clear? So we are taking this section n at a distance of, let's say, very infinitesimal distance, that is dx, and dx tends to 0. Okay, so this is n. Let's say again draw a tangent here also. So this tangent will make another angle like this. Okay, so let's say this was your curve, this was your m, this was theta. Okay, and now this is the tangent, and here this is like this. So obviously this is another theta. Let's say this is theta 2. So the angle caused by tangent at n is theta 2, and there is a difference. Let's say theta 2 minus theta 1 is d theta, and again draw a perpendicular both at m and n. Okay, this was our curve, and this was one tangent, this was another tangent. We are drawing a perpendicular at m, a perpendicular at n. Okay, they will meet somewhere. Let's say they are meeting at this point. Okay, so this is n, this is m, and the difference between these two angles, this is theta 1 and this is theta 2. D theta is simply your theta 2 minus theta 1. Okay, and if we draw perpendicular, this is 90 degree, this is also 90 degree, so this angle become your d theta, or the difference between these two angles. How? Well, in the case of bending moment lesson I have already discussed. Again let's say this is theta 2. Okay, and this is your theta 1. Okay, so what is this difference? This difference is your d theta. Simply this is d theta, and this angle becomes 180 minus d theta. This is 90 degree as it is perpendicular, this is also 90 degree, this is also perpendicular, so they becomes 90 degree and 90 degree. What is this angle? Well, 360 minus 90 minus 90 minus 180 plus d theta, so this angle becomes d theta. Well, let's say this curve, or the distance between m and n in curvilinear path is ds. Okay, and this angle is theta, d theta, so this is d theta. And if this radius of curvature is r, okay, so the radius of curvature is r, so we can say that this is n, this is n. We can say that this curve ds is nothing but r times d theta. Clear? So from here we can say that 1 by r is equal to d theta by ds. Okay, and in practical case what happens? we have considered this curve. This was M, this was N, okay, and we have measured in horizontal direction, in this direction, and it was dx. In practical reason, the deflection is very much small, okay, not equal to 0 but very small. That's why this is our assumption that this dx is almost equal to ds. That means straight path is almost equal to your curvilinear path. This is our first assumption. Not only that, when we measure, if this is your curve, okay, this is ds, so let's say this is dx and this is dy. So at this point, if we take any tangent, let's say it makes theta, so tan theta is your d, let's say this is your theta, so tan theta is equal to simply dy by dx, height, and this is base. And also, as theta is very much small, we can say tan theta is equal to theta, that is dy dx. Okay, so this is our second assumption. First assumption is curvilinear path is almost equal to straight path, and your theta is equal to tan theta, because theta is very much small, and from here we can calculate theta, that is dy by dx. Okay, so what is now 1 by r? 1 by r is now d theta by dx. Instead of ds we are writing dx, and theta is dy by dx, so d dy dx by dx. That means 1 by r is d2y by dx2. That means second order derivative of deflection, that is y. Again, 1 by r is m by I, m by ui, so m by ei. Okay, m by e. Now here you can see that your, if this is the curve, make it stiff for better understanding. Let's say this is your curve, so here is tangent, this is original beam. Okay, so this is theta. Now we are proceeding towards x, that is positive. Okay, but at a distance of dx or at a certain interval, take another tangent. Let's say this is tangent. So now these are two parallel. So can you tell me which one is bigger, which angle is theta 1 or theta 2? Of course, theta 1 is steeper than theta 2. That means when x is increasing, your theta is decreasing. That means d theta dx, or this term is actually negative. Okay, this is negative, so here we should put negative sign. This is also negative, this is negative, and this is become negative. So now we can write that, sorry, this is not negative because 1 by r is this one. So we can now write that d2y dx2 at any section of the beam is equal to minus m by ei. Okay, this is also $1 million equation. Okay, now let's say we have an cantilever beam like this. Okay, and there is a point load acting at the free end. Length is L. So the question is, what is the deflection at this tip or at this free edge? It will deflect like this. Okay, this was your actual beam. The question is, what is this deflection, or what is this y? You can use this equation easily to find this y or delta, whatever. How? Well, we know d2y dx2 is equal to minus m by ei. Now what is m? At any distance, let's say at a distance of x from free end, we are considering moment. So what is moment at a distance of x from free end? Simply p times x. Okay, so it becomes minus px by ei. Ei is your constant, load is also constant. Only variable is x, which varies from 0 to L. So if we integrate both sides, it becomes d2y dx2 is equal to minus p by ei integration of your x, and at the left side we will integrate with respect to dx or length at the right side also. So left side becomes dy dx is equal to minus p x square by 2 ei plus integrating constant, that is c1, and this dy dx gives you the slope here or the tangent. This is your theta at this end, and when you apply x is equal to 0, you will get this theta. Well, what is c1? This is your theta, but at the fixed end or when x is equal to L, this theta is equal to 0. So put it becomes 0 is equal to minus pl square by 2ei plus c1. So c1 becomes pl square by 2ei. So the equation for your slope becomes this one, minus px square by 2ei plus pl square by 2ei. Whenever you put the value of x, you will get the deflection at that section. Okay, so this is the equation for your slope in this type of beam and loading. Now if we again integrate this with respect to x, you will get your dy dx is equal to integration of pl square 2ei minus px square 2ei. Okay, again integrate it, you will get the equation of deflection or y is equal to pl square x divided by 2ei minus px cube by 6ei plus integrating constant c2. Now what is the value of c2? Again, for a fixed end beam, at the fixed end or when x is equal to L, your deflection is 0. So c2 becomes 0 is equal to 0, put x is equal to 0, and here is also x is equal to 0 plus c2. So c2 is 0. So the equation for your deflection becomes y is equal to pl square x by 2ei minus px cube by 6ei. Sorry, here we have put x is equal to 0, but it should be x is equal to L. So correct it at the left side. At fixed end or at x is equal to L, deflection is 0, so it is 0, and here pl square into L, so it becomes pl cube divided by 2ei minus pl cube divided by 6ei plus c2, or c2 becomes your, this is 6, this is minus 3, and this is minus plus 1 pl cube by ei. You can check it yourself. c2 becomes your minus pl cube by ei. Okay, yes, PLQ by 2 EI. So the equation for deflection becomes C2 is equal to minus PLQ by, sorry, this one 3, this is 3, PLQ by 3 EI. Okay, and here one more thing, the moment here caused by a point load at cantilever beam is hogging in nature. That means tension at top, compression at bottom. So you have to also consider this sign convention for moment, which we have not. So M becomes negative, this is negative, this one negative, okay, which creates positivity, this is positive. And also from here C1 becomes negative, here this is negative, okay, and this is positive. Once you correct for everything, you will get this one, this is. So at this free end, when x is equal to 0, what is the deflection? Delta at free end is equal to, put x is equal to 0, you will get, this is PLQ by 3 EI. This is positive. As per our sign convention, this was x as positive, this was y as positive.